Hi everybody, this is Nafish. In today's lecture, we're going to go over the simulation and extraction of range information from an automotive radar. Okay, so we are going to first generate some transmit chirps and then add some delay to it to create the receive chirps, and then we're going to mix it out and get the IF signal, and we are going to convert it to the frequency domain to get the range information from it. Okay, and we are only going to focus on the range of the radar. Usually the radar provides a range, Doppler, and angle information, but in this simulation we're just going to focus on the range information extraction. Okay, so imported numpy and matplotlib, and let's create the ramping signal. Okay, so let's say our frequency start is 76 gigs, and in automotive radar usually the band is from 76 to 81 gigs. Okay, in this case I'm taking the starting frequency 76 gigs and stopping frequency 77 gigs, so we have a bandwidth of 1 gigs, right? And let's say we are starting the chirp at 0 seconds and stopping the ramp at 40 microsecond. Okay, and from there you can say like our total chip time is t stop, just putting it into equation, minus t start, right, which is 40 microseconds. Okay, so this is our total chip time, and also we have to define our time vector. Okay, so time vector is need to take the lint space np dot lint space. Okay, and then the start time of the chip generation, stop time of the chip generation. Okay, and um, how many samples we're taking. So let's say n is the number of samples and define n here. Let's say we have 10,000. Okay, so these are our initial parameters. So basically this f start and stop, these are two inputs to the ramp generator. Okay, and when you provide these two inputs, this ramp generator is going to provide you the output frequency, which is, I'm going to provide the equation right here, which is f out is equals to f start. So we are starting at 76, and then the bandwidth. Okay, so bandwidth is nothing but f stop minus f start. Okay, and this term is going to be multiplied by the time vector over tc, so basically the change of the slope. Okay, and the whole thing is divided by 2. So this is the equation of the frequency output of the linear frequency modulated generator. Okay, so let's run this. And like I'm talking about chip is nothing but a sinusoidal wave. Just going to show you right here. Okay, so let's say our transmit signal tx is a times cos, then 2 times pi times f times t. Okay, so if you look into this equation, this is just a sinusoidal wave equation, right? So now let's define a, which is the amplitude. In this case I'm just taking 1 volt. Okay, and cos, this term we have to write np dot cos, and then also for pi np dot pi, because importing these two terms from the numpy library, right? And f, the frequency, is nothing but the frequency change we have from the ram generator, right? So that's f out. And in lfm we are kind of going to increase or decrease the frequency over time, right? Just going to show you in a bit in the plot. So if we run this, I hope there is no error. Yep. And then let's plot it out. Plt.plot. We have x, right? So these two in a rounded bracket, and haven't defined c yet, which is the speed of light. So c is 3e8. Okay. So this is our time delay. This much time the signal takes to be received in the receiver. Okay. Oh, I haven't defined d as well, which is the distance. It's 50 meters, right? Okay. So we have the time delay here. Now, the received signal Rx, it's same, exactly the same thing as the tx, but we need to add the time delay. Okay, and to add the time delay, before we do that, we have to fix this frequency as well. So the frequency component, just copying the output of the lfm modulator, here we have to add time delay in right here with the time vector, so tau. Okay, and putting it in a rounded bracket. Okay, and we are going to copy this this transmit signal tx right here, and going to paste it here. Okay, so it's the same equation, but this frequency here is going to be replaced by this one. Let's change the variable name frx, let's say, and this f out is going to be changed or replaced by f rx. Okay, and this t here need to add time delay as well. Okay, so we have compensated for the time delay here, meaning we have introduced the time delay into the signal, which is going to create a phase shift. Okay, so let's run it, and also let's visualize the signal. Okay, and to do that, I'm just going to copy the entire part here, the plotting part. Okay, here I already have rx, so just removing these two things. Okay, instead of tx, plotting rx. Okay, and then plot it out. Okay, so this is our receive signal. Okay, and this is what we are transmitting. This is the receive signal. Okay, now we have to find the if signal. Okay, so for the if signal, which is the intermediate frequency signal after we mix the tx and rx. Okay, so if signal is nothing but it's also a sinusoidal signal. So we have to write down the amplitude, assuming like there is no loss in the environment. Okay, so we are getting the all the signal back to the rf end. Okay, so np dot cos. Okay, so we have the same sinusoidal signal, but here we have to write down, basically it's going to be the rx minus tx of the angular frequency. Let me write it down first and then put um, the equation. So angular tx, so basically angular rx, which is right here. Okay, this guy. So need to copy the entire part here. Okay, and then we are going to get the phase shift. Okay, that's going to be key for this if signal generation. Okay, so replacing this guy with the received phase shift right here, or angular frequency, and the transmit side we have right here, this whole part. Okay, copy that and paste it right there. So this is the basically the difference in the, or difference of the phase shift we are getting. Okay, so if I run this, and again I'm taking this part and copying and pasting it here, and basically here I'm plotting if, right? Okay, and oh, this is going to be the variable name if sig, so let's plot it out. So basically you see this is a down converted wave. You can uh, plot it up to 40, maybe 40 microseconds, try to see what's going on. Okay, so after the mixing you are getting this is sinusoidal wave. Let me put it down to 20 microseconds. Okay, okay, this is what we are getting after the mixing. So now we have to apply fast Fourier transform on this if signal. Okay, so if sig and then FFT is nothing but calling that um, numpy FFT. Okay, and then if sig. Okay, so this is the FFT we are getting here, and also we have to calculate the frequency. Okay, because this is all in time domain, right? So the frequency, for the frequency we have we can also call that FFT fric from numpy, and then the input is the number of samples and the sampling rate. So in this case we have um, 40 microseconds, right? We have the total duration of the signal and the samples are distributed over this amount. So this is the sampling rate we have. Okay, so you get the frequency as well. Okay, um, oh, I think I have to put another FFT here, right there, and then it should work. Okay, let me write it down again. np dot fft dot fft fric right here. Okay, this should work now. So I have the frequency. Okay, but one thing I would like to show is, the order. So starting at 0, okay, but then it's ending at minus 25,000. Okay, so basically I have to sort out the arguments here. Okay, because it should be minus 25,000, then 0, and then 25,000, right? So let's sort it out. To do that, let's say id index is np dot arg sort, and then this fric. Okay, if I run that, and then our new fric will be nothing but the sorted arguments, right? So this one. Okay, and apply the same thing on this if signal FFT as well. So sort out that one also. Okay, and idx. Okay, so I'm just sorting out with the values. Okay, so let's run it, and let's now it's time to plot out the signal. So let's say PLD dot plot, and we have the FIC in x-axis, and we have the IF signal, right? So IF signal FFT, and I have to take, since it's an FFT, I have to take the absolute value to avoid the complex numbers. So taking the absolute value, okay, and I think there is one rounded bracket there. Okay, so I can see the plot right here. It's still in frequency domain. One thing we can do is just look into the positive side, okay, and also we can do the normalization of this plot and convert this axis um, to range axis, okay, to retrieve the range information. Okay, so let me copy this entire thing, and maybe I can do it right here. Okay, so range is nothing but we have the freq, right? This frequency times c, and then that's going to be divided by the slope, 2 times the slope, so 2 times t. I think the slope rate is going to be the bandwidth, which is f out minus f, sorry, f stop minus f start, and that's going to be divided by tc. Okay, so I guess this is right, this equation, and put range right here. Okay, so this is our range axis, so converting that frequency axis to range axis. Okay, and then here I have to normalize as well. So let's do the normalized part right here. So basically you are dividing by the max of this absolute value. Okay, and then run it. One more rounded bracket. Okay, so this is our information we're getting here. I can just zoom it a bit. So PLD dot axis, and just let's only focus from 0 to 100. Okay, so 0 to 100, and then our y-axis is 0 to 1. Okay, let's run it. Okay, so this is our, because you can see this is right in 50. Okay, so this peak is indicating that we have a target at 50 meters. Okay, and this axis is in range. We have converted that into range right here from this, using this equation. I can now change the target distance. It's 50 meters, right? I can make it 80 meters and try to see where it's popping up. So run everything again. It's going to take a bit, and you see it's moved to 80 meters. Okay, so this is how we can simulate a radar target, and you can also add some noise to see how this is performing, how the FFT is performing. We can do a lot of things here.